Okay, excellent. So reminder here, homework 2 is due Monday, 9/14. So if you haven't started that, make sure you start it. We'll go over some of those problems today, and then also we can talk about them. Well, we won't talk about them Monday because we won't be here Monday. We'll talk about almost all of them today, so then if you have any questions, just send me an email and we can meet that way. So make sure you check announcements for the schedule, just to give you a little synopsis if you haven't seen that already. Thursday will be Group B meeting for lab, so Group A does not meet this week. And then Monday, I will make a video over the weekend, so we'll have Chapter 4 information that way. So we will not be meeting next Monday, but we will be meeting on Wednesday. Okay? And then the lab next week, it's an online lab, so you won't have to come in for that. And more information you'll have this week. So it's asynchronous. You can do it whenever you want to. The lab for the following week. Okay? Good. Do you have any questions? Good. I thought we could just start with some couple of problems from the homework. Just to remind you what we ended up doing last time. We had motion on a ramp. Okay, that looks pretty good. So here, gravity was straight down, and it looks kind of like this. And if this is theta, we saw last time that this angle is also equal to theta. So it is two-dimensional motion, but we've made it into a one-dimensional motion problem. So really, as this slides down, it's moving both in the x direction and the y direction. Our goal is to make it into a one-dimensional problem where it's only moving in this new x direction. And we saw last time that the acceleration in the x direction just turns out to be g sine theta. And that works out pretty nicely too in terms of the formula. When theta is 90 degrees, the acceleration is just free fall, 9.8. And then when theta is 0, there is no acceleration, it's just flat. So anywhere in between 0 and 90 degrees, as the angle gets bigger, acceleration gets bigger all the way up to free fall. Okay? So I thought we could first of all take a look at a couple of problems. So today we'll finish off Chapter 3. That's the plan for today. Finish off two-dimensional motion, and then spend some more time working on the homework questions. And then any questions that you have. Okay? So let's take a look at some of these homework questions. Good. So this one is kind of like the Wilmette ski problem that we saw last time. You begin sliding down a 15-degree ski slope, just like the diagram that you just had. Ignoring friction and air resistance, how fast will you be moving after 10 seconds? Okay, so let me write this down, and then we can look back at what I'm writing. Theta is 10 degrees, and we're asked how fast will you be moving after 10 seconds. All right, let's go back to this view. Okay, good. 15 degrees. Oh yes, thanks Rick. And 10 seconds, okay. Good, so the motion is right down the incline here. We could figure out what the acceleration is. It's g sine of 15 degrees. So that's something that we know. I'll put a little check mark there. Okay, good, and then we want to know how fast we're going after 10 seconds. So it's kind of like this. We go down the incline this direction. We don't know how far we go, but we know the acceleration, and we know how much time we have. And we're ignoring air resistance, so this is the situation we have. And one thing that we're assuming is that we're starting at rest. So the initial velocity is equal to 0 then. That's another piece of information that we have. Okay, so we've got all three kinematics equations. It looks like the first one will actually work for us. Later velocity is equal to earlier velocity. plus a times t. And now we know everything. The initial velocity is 0. Okay? So without putting numbers in, that's the way that you do it. As far as the acceleration goes, it's going to be in meters per second squared. We're multiplying it by seconds, so the answer comes out in meters per second, which is what actually Mastering Physics wants. Yeah? The way I've set it up is just to get the magnitude of the acceleration. So the acceleration is just this way. So it's not negative. We're just looking at the magnitude of how much it is. The negative would mean like, because this is the x-axis, negative would mean it's accelerating back that way. So I've set it up that this is the positive x direction. It would be positive, yeah. Yeah. Let's see how they actually word it. How fast will you be moving? So they really don't say, well, how much is the velocity? So here we're just really finding the speed. Okay, yeah, good. Any other questions on that one?
How would you work out like the g sine of 15 degrees?
So yeah, let's take a look at that. So this would give us 9.8 meters per second squared, and then times the sine of 15 degrees. So make sure your calculator is in degree mode and multiply those together. Okay, excellent. Does that answer it there?
Yeah.
Okay, very good.
Yep.
Okay, you're welcome. Did anybody have a number for that? I'll write it down so you can double check. I found my calculator over the long weekend, but I forgot to bring it, so. 2.5, okay. That's a believable number. Anybody else confirm that? Excellent, very good. All right, good. Any other questions on that one? All right, let's look at one more of these motion on a ramp problems. Soapbox derby. Participants build non-motorized cars, very low friction. Cars race down a rolling hill, assuming that the track begins with the 47-meter long section tilted at 16 degrees below the horizontal. What's the maximum possible acceleration? Okay, so the first part is just like we just did to figure out the maximum acceleration. Oh, I'm sorry. Okay. Yeah, always yell at me because I'm getting used to flipping between different things. So this is the picture. This is the fifth one on the homework. So it's from chapter 3, if you look at the back of the book, number 18 from the back of the book. Okay, good. So soapbox derby, 16 degrees below the horizontal. The track's actually 47 feet long, and then we want to know the maximum acceleration. So that's just like what we did with the previous one. And then if you start from rest and undergo this acceleration, the full distance, what is the final speed? Okay, so this one is similar, part B is similar to what we just found. We don't know how long this takes, but we know the distance that we traveled through. So probably it's going to be a different kinematics equation. Okay, back to the document camera. So really, it's the same picture. This is 16 degrees. That's what they actually tell you in the problem, 16 degrees below the horizontal. So that means that this one is also 16 degrees. And then the car goes down here. In my problem, you might have a different number, but mine is 47 feet. Perfectly good number, but as you know, that's not an SI unit. We'll have to convert that to meters. Okay, but luckily, they give us the conversion factor. 1 meter is 3.28 feet. Okay, and starting from rest. And then what's our final speed? Okay? And really, the displacement that we have, we'll have to do a little bit of work, but it's 47 feet. And then we know it's 3.28 feet per 1 meter. So the feet cancel out, and then we're left with meters. So what do we get for that, actually? 14.32, you say? 33, okay, we'll go with that. All right, good. So part A, maximum acceleration, g sine of theta. So 9.8 meters per second squared, and then the sine of 16. So this is for part A. So that'll just come out to be some number. So without actually punching it in, that's how you do it. And then we've got the 3 kinematics equations to use. So in this one, we don't know the time. They don't give us the time. They do give us the displacement, though. So really only one of the kinematics equations doesn't have time in it. Let me write it down and see if it will actually work for us. Final velocity squared is equal to initial velocity squared plus 2a delta x. So can we actually use that to get the speed after we've gone through this 14.33 meters? Yeah, we can. Yeah, we know everything other than what we're looking for. The initial speed 0, we know that. We just found the acceleration, we know the displacement. So we can do that. Okay, so this part is 0. Final velocity squared, 2a delta x. And then I'll take the square root of both sides and finally end up with this. So as far as units go again, the acceleration is going to be meters per second squared times meters. So then we have meters squared over seconds squared, but then we're taking the square root of that, so we get meters per second. So I'll just put a check mark there. I'll leave it to you to finish that up, but that's the way to do it. Now you could have done it a different way. You could have used the first kinematics equation to figure out how long it takes to go. Well, no, you can't really do that because you don't know the final speed. The first one actually won't even work for you. So probably you have to go with it this way. So maybe the second one. It's just interesting to think about this stuff. This is the second kinematics equation we had. You could have used this. I'm just showing you another way of doing it. You could have used the second kinematics equation to figure out how long it takes to go that distance, and then use the first one to figure out the final speed. So a couple different ways of doing it. Probably the way we did it is the quickest way. No points for speed, though. Okay. All right, any questions on this one? All right, so let's continue on then. We'll do some more projectile motion type problems. This is just really a two-dimensional problem we made into a one-dimensional problem. Now we'll really start getting into some other stuff. Okay. Now the most difficult thing for these kind of problems is things are happening in 2 dimensions at the same time, but you can analyze the x motion completely independent from the y motion. So projectile motion is an extension of 2-dimensional free fall motion. So we'll have what we did before in chapter 2. The acceleration in the y will still be negative 9.8. We're assuming there's no air resistance. The acceleration in the x direction will be 0, though. So if you did the lab last week, group A, this is the sort of thing that we did. Group B, this is what you'll actually do this week. So here's a physics educational technology thing we can take a look at. Whoops, actually I didn't want that one. Maybe it's this one. Yep. also, we get to try to hit the target with this. So we can take this. And we could adjust where it's going to go. There's a way to put the guy in here, but I can't remember what it is actually. So you have the notes, you can kind of play around with it too, figure out how to actually shoot the guy. Somewhere here. So we want to try to hit the target, and you could hit the target by adjusting the angle or the speed here. So let me just try 61 degrees and see what happens here. Okay, so still too far. So what could I do to try to actually hit the target? I could do a lower speed. Yeah, let's try that. Let's leave the angle the same, but make the speed a little bit lower. Maybe 12. Oh, not quite enough. Yes, okay, good. So with this combination of 61 degrees and 16 meters per second, you could actually hit the target. There's actually to hit that target, there's two different angles that you can get to hit the target. So right now we're kind of like this. We could actually make the angle a little bit shallower and hit it if we did it that way too. So we're going to come up with something called the range equation that will actually allow us to predict this. So changing the angle, changing the speed, but also you could change gravity. So if you were on the moon hitting a golf ball, you could hit a golf ball 3 times as far. What's a good golf ball distance on Earth? I have no idea. Anybody play golf? Oh, let's do baseball then. So if you hit a baseball, you could hit it, if you're a professional player, 400 feet maybe. On the moon, just pretend you hit it like 1,200 feet. So you could, if you're at Wrigley Field, it goes way, 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 way out there. So that would be pretty cool to do, and astronauts actually did that on the moon, hit golf balls. So it depends on the speed, the angle, but also where you're at here. So let me change this to the moon, something like around 3 or so. Oh, it doesn't even go that low. All right, well this is about half as much as we have on the Earth now. So completely out of the picture even. So if this went about 22.9, if I cut gravity in half, it's going to go even farther. Okay, so we'll come back to this. I just kind of wanted to let you see this in the beginning. If you had to guess, what do you think would be the maximum range? If you wanted to get the greatest distance, what angle would you go at? It's just a complete guess. What is it? Somewhere between 0 and 90, what would you pick to get the maximum distance? 90. Was it? 90. 90, so that, if it's 90, that would just go straight up. Oh. So to get the greatest distance this way. Any guesses? Don't be shy, it's just a guess. To me, if I was just going to, I know the answer, but I would say, well, 45 seems like it might be the best way, right? Because you're not shooting it way too high, you're not shooting it too shallow. 45 might be the best angle to get the greatest range. We're going to see that that's actually true in a few minutes too. Just to kind of show you. Actually, I think this might get rid of all the old stuff. Yep. And we're back to 18. Okay. Okay, so let me make the angle a little bit greater. Not quite as far. Let me make the angle a little bit less. If you notice, those actually hit at the same spot, right? There's a couple of angles where you get the same range. So 45 is the greatest. And we'll see why mathematically that is too. Okay? Any questions on this? I'll have to try to figure out how to put the guy in there too. I used to be able to just pick him up and throw him in there. but not anymore. Okay, so this is what's coming up, these kind of range things. Now this is going from one level back to the same level. That's kind of a special case. It doesn't have to be like that. It could be a situation where you're like playing darts. So if you're playing darts, the dart is not only moving horizontally, it's also moving vertically. So that would be projectile motion too. It doesn't have to be one of these same level to same level kind of problems. Okay. You have a lot of good entertainment coming up today. So imagine this. You take a ball and you drop it straight down. At the same instant, you shoot a ball horizontally, so completely horizontally. Which one do you think would hit the ground first? So you drop one, at the same instant, you shoot one horizontally. Which one would hit the ground at the same time? What's that? Same time, okay, good. Any other ideas? Oh, let me make it a little more extreme. Say you shot a bullet that way, horizontally, and at the same instant you dropped a bullet straight down. Then which one do you think would hit the ground first? The straight down one, because the bullet's going to probably, seems like it would stay in the air a lot longer. Okay, so that's our intuition, I think, tells us that. Let's take a look at this.
If my exam was learning this, I would be all over it. What the
These are the Mythbusters.
What you got there?
This is a good one. Picture two bullets, each exactly the same distance from the ground, each released at the exact same second. One bullet is dropped to the ground, the other is fired from the gun. The classic physics law experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Whoops.
Based on the theory that the bullet that's fired from the gun has no wings on it, no lip. Thus, gravity has the same effect on it as it does on the drone bullet, and thus, they hit the ground simultaneously.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, so you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh yeah.
You never make predictions. That's awesome.
Bullet drop versus fire. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Oh, I can't wait to see the high speed.
Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual movies, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24th of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24th of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
Okay.
Dish. Most name brand bars.
So why was that exactly? So the key really is that the initial velocity in the y direction is the same because you're shooting one horizontally. So the initial velocity in the y is 0. And then you drop one straight down. So the initial velocity in the y is also 0 for that one. The displacement in the y direction, so that's the ground. The displacement in the y direction is the same for each of them. So this is the same. The acceleration in the y, it's the same, right? In the y direction, although the bullet that you shoot horizontally initially just is traveling in the x direction, then it starts to travel in the y direction because of gravity. So same initial velocity in the y, which is 0, same displacement, same acceleration in the y, is going to give us the same time. We could look at this kinematics equation. Now this is for the y direction. So this is 0 for both of them. So I can multiply both sides by 2, divide by the acceleration in the y. And that's t squared. And then take the square root of both sides. And that's the amount of time. So the time is the same for each of them. It doesn't seem like that should happen, right, in our everyday experience in life, but it turns out it does if there's no air resistance. Okay? Excellent. Any questions on that? So let me just give you a little synopsis then of projectile motion. So I'm going to break it down x direction versus y direction. So in the x direction, the acceleration is 0. The only thing that we have to work with in the x direction is this. Okay? That's it. That's the only thing that we have. In the y direction, we have this. Acceleration in the y, negative 9.8. So although these projectiles, or whatever they are moving in 2 dimensions, you can analyze the x motion and the y motion independent from each other. And then in the y direction, you have all the kinematics equations to work with. So that's the first one. Here's another one we can use. And then finally, this one. Okay, this is an A, believe it or not. Okay, so in some sense, the x direction is easier because that's all you have. On the other hand, it's limiting because that's all you have. You don't have a lot to work with in the x direction. You have more to work with in the y direction. Now, what ties everything together is the time. Whatever happens in the x direction, it's the same time as what's happening in the y direction. So sometimes you have to use y direction information to get something to use in the x direction, for example. Like you might have to use the y direction stuff to be able to figure out the time and then use that time over in the x direction. So really it's just what we've done before, but now we're doing twice as much, really, because we've got 2 different directions. Okay, good. So remember that's projectile motion. We'll definitely do some problems on that. So this one, you know the answer because you just watched the video. Okay. Right, which one hits the ground first? Now, a heavy red one versus a lighter orange colored one, the mass doesn't matter at all. So if they hit the ground at the same time. So if you drop one or one goes off at some different angle, as long as the initial velocity is horizontal, it says horizontal there, they will hit the ground at the same time, just from what you saw before. The mass doesn't matter. I think you saw me drop like, maybe I had a quarter versus $1, different masses, so the mass doesn't come into play. Okay, good. So the people that did the lab last week saw this. You'll see it if you didn't do it yet. In the x direction, the velocity is not going to change. right? The acceleration in the x direction is 0, so the velocity doesn't change. The velocity in the y direction does change, though. So every second, it decreases by 9.8 meters per second squared in the y direction. That's the hardest thing about projectile motion, realizing, I think, that you have to do the x and y independent from each other. Okay. There's one other thing we can take a look at. We'll come up with something called the range equation. So it's for this picture. So we want to be able to predict the range. This is just what you saw. If something goes like this, this is theta. This is the overall velocity. So it has an x part and a y part. The x part is this part of it. The velocity in the x turns out to be the initial velocity times the cosine of theta. Now when you read through the chapter, you'll notice that it'll say initial velocity in the x direction. I just call it x velocity. It's not going to change, so calling it the initial velocity implies that it's going to be different later on, and it's not. The x velocity is going to stay the same. If you want, you could actually write this, or do the picture, but maybe write it up there if you want to. Maybe the picture's better, actually. Now the y velocity will change. So the initial velocity in the y direction is the overall velocity times the sine of theta. Okay? So if you have this picture, kind of like the launch one that we did, this is the x velocity, this is the initial velocity in the y direction. One thing that you can use for this situation is at the highest point, the very highest point, the y velocity is 0. So sometimes in problems you have to bring that into the problem yourself, that at the peak, the y velocity is 0. Okay, we'll have to get some practice doing problems with that. Okay, and then finally let's get something called the range equation. It's called the range equation because that's this distance. So it's usually called the range equation. We've been calling it delta x before, but it's the same thing. The range is delta x. So what I want to do is to be able to predict the range, this distance, just based on the overall velocity and the angle. So just based on the overall velocity and the angle, I want to be able to predict how far you can maybe throw a football, for example. So if you throw a football at a certain angle, a certain speed, how far is it going to go if there's no air resistance? Okay, what we can do is start with the x direction, right? That's what I'm calling the range. So let me get a new piece of paper out. So just a little bit of algebra. The range is the x velocity times the time. That's not really what I want yet, right? I want the range, but I don't want to know the x velocity or the time. I want the overall velocity and the angle. So let me plug in what I know the x velocity is in terms of the angle. Okay. So I'm getting closer. There's the overall velocity. There's the cosine. I forgot to write theta. And then multiply that by the time. But I don't want to have to measure the time again, so I'm going to have to eliminate time from the equation. So maybe I could use the y direction to get the time. So here's all the kinematics equations that I had. So at the highest point, if you remember, the highest point, the y velocity was 0. So let me actually use this kinematics equation to eliminate time. You're not going to have to do what I'm doing now every time. I'm just showing you where this equation comes from that you'll be able to use. So I'm using this equation, and at the highest point, the velocity is 0. Okay, so highest point I'm looking at. Final velocity, I know it's 0, I just wrote it to be complete here. Initial velocity plus acceleration in the y times the time. So at the highest point, this is 0. So if I can get the time for the highest point, if I multiply that by 2, that's the total time. So this is just the time at the highest point. So I'm going to call it t prime, like time to get to the highest point. So T for highest point. Okay. So this part is 0. I want to solve for the overall time and then plug it back into this equation and get rid of time that way. So that side's 0. I'm going to subtract this from both sides, divide by acceleration in the y, and that's t prime. That's the time to get to the highest point. So if I multiply that by 2, that's the overall time. So I'm going to multiply this equation by 2. That gives me the overall time. So minus 2 initial velocity in the y divided by, and I'm going to stick the negative 9.8 in here now. And then the negatives actually cancel out, which is good. Okay, so this is the total time. I'm going to take this and eventually plug it back into this formula. Let me just do one more thing to it though. 2, and I'm going to do initial overall velocity sine of theta divided by 9.8. Okay, so I've, instead of having initial velocity in the y, I'm writing that in terms of the overall velocity and the angle. Okay, good. So now finally let me plug this back in up here. So range, here's what I have so far. Initial velocity cosine theta, and now instead of having t, I'm going to plug this whole thing in. 2 initial velocity sine of theta divided by 9.8. It's not in its final form yet, but it is what I wanted. There's the range just based on the overall velocity and the angle, right? So if I know the overall velocity and the angle, plug it in, and I can solve for the range. I can clean this up a little bit, though. Let me write it like this. So I've got initial velocity. Remember, that's the overall velocity. So it's squared, and then 2 sine theta cosine theta divided by 9.8. Now there's a little used trig identity. So think back to when you did trig identities, like double angle formulas. Remember all that kind of stuff? Half angle formulas. You remember it when you're doing it, but then if you don't use it, you remember doing it, but you don't exactly remember what it was. But maybe you'll remember this one. 2 sine theta cosine theta is equal to something. Do you remember what? In like 15 years of me asking, nobody's ever remembered it. So if you ever did half angles and double angles, literally nobody in the last 15 years here has remembered this. Here or even in West Lafayette. It's equal to the sine of 2 theta. Initial velocity squared sine of 2 theta. So this whole thing is equal to this. And then divided by 9.8. So that is the range equation. The range is equal to the initial velocity squared sine of 2 theta divided by 9.8. So if this is smaller, like it is on the moon, the range is bigger. Okay? The faster you go, the bigger the range, and it's actually squared in the formula. And now you can see 45 degrees actually does give you the biggest range. So that would be the sine of 2 times 45. The sine of 90, that's as big as the sine could be when you're taking the sine of 90. So 45 degrees gives you the largest range also. Okay? And there's a couple of angles where you get the same exact range as you saw in the FET 2. Yep. Is that back over here maybe somewhere? So this t prime is just the time to get to the highest point. The overall time, you have to multiply it by 2 to get the overall time. So t prime is to just get to the highest point, but we're coming all the way back down. So if you take this time, multiply it by 2, you get the total time. The total time of flight. Okay? Yeah, good. So I can actually add this to the to our little piece we have here. XY direction, you have this picture, this part here, and let me just add range. Initial velocity squared sine of 2 times theta divided by 9.8. So this is called the range equation. Only good for this situation. You could do it without having the range equation, but it just makes your life a little bit simpler. Good. I think that's everything you need to know for projectile motion, actually. Okay. Any questions on that? I think we need to get some experience with it, right? Okay. Bam, bam. All right, excellent. So this is kind of what we've gone through, but here's a nice graphic way of looking at it. There's the overall velocity. It has an x part, it has a y part. If you notice, the lighter green is not changing. So if the x velocity is 10, the x velocity is staying 10 the whole time. It's the y velocity that changes. At the highest point, the y velocity is actually 0, and if you start off here with 19.6 in the y direction, when you get back to the same level, you're at negative 19.6. Okay? So keep that picture in mind when we're doing some problems. Okay? And then if you have the overall velocity, you could break it into its parts. The x part, as you notice, it says initial velocity in the x. I always just call it x velocity again because it's not going to be changing. This one here. Right, that's what I just called the just x velocity. Okay, same thing, it's just free fall in the y direction and no acceleration in the x direction. Everything just happens at the same time though. Okay, so when it says my take on it is that x and y column thing that I built. Okay, so really we're just using the kinematics equations that we had before. So this problem is similar to 3.27. So I thought we could do this dock jumping problem and then also do 3.32. So in the sport of dock jumping, dogs run at full speed. Maybe you've seen videos of this actually. Run at full speed off the end of a dock that sits a few feet above a pool of water. The winning dog is the one that lands the farthest from the end of the dock. So have you seen this before? I think on like ESPN, if it's a slow day, they'll show this happening. Like dogs run, jump. There's a certain distance in the y direction, and whichever dog gets the farthest is the dog that wins. So if a dog runs at 8.5 meters per second, straight off the end of a dock, that is 0.61 meters, about 2 feet above the water, how far will the dog go before splashing down? So you see the picture there. Here's the dog running horizontally. So horizontally means that the initial velocity in the y is 0. So it would be nice if they just said that, right? Initial velocity in the y is 0. But horizontal means initial velocity in the y is 0. Now the displacement in the y direction, the distance is 0.61, but the displacement in the y direction is negative 0.61, right? Because in the y direction the dog went down. Acceleration in the y, negative 9.8, acceleration in the x, 0. And we want to figure out how far over the dog landed. So what we can do is figure out how long it takes the dog to travel 0.61 in the y direction. So how long does it take the dog to go 0.61? Remember from the video you saw, it doesn't matter if the dog drops straight down or goes horizontally. It's the same amount of time to hit the ground, hit the water in this case. So we can use the y direction to figure out the time, and then knowing the time and the x velocity, that's what this is. Oops, this is the x velocity. So if you knew the time and the x velocity, which is not changing, then you could figure out how far the dog moves over. Okay, so let me do that then. Yes, okay, good. So the tools that you have are, that little sheet that we built earlier. So initial velocity in the y, 0. Acceleration in the y, negative 9.8. Displacement in y, really negative 0.61, because in the y direction, the dog has moved downward. So I'm going to use the y information to figure out the amount of time it takes to hit the water, just thinking about this going in the y direction, and then use that time to figure out how far over I go. Okay, so remember, you have all those kinematics equations to use. Let me put them back here. Okay, so we're trying to figure out the time. Well, the first equation has time in it, but we don't know the y velocity right before the dog hit the ground, so this one actually doesn't really help us. The second one, again, we're trying to figure out time, so the second equation does have time in it. Okay, so we do know the displacement in the y, initial velocity in the y, 0, acceleration in the y. So we could actually use the second one to figure out the time it takes to fall that distance. So let me rewrite it here. So initial velocity in the y is 0. Now if you notice, whenever I do these problems, almost always, I wait until the end to put the numbers in. The reason I do that is I don't want to accidentally write a number incorrectly. It's easy to write a number incorrectly. It's harder to write a variable wrong. I'm not going to all of a sudden call acceleration j or something like that. Right? So I wait to the end and then I put numbers in. You could do it however you want. That's the reason that I'm doing it. That's the motivation for me doing this. Okay, so that's 0. I'm trying to figure out the time. So that's 0. Multiply both sides by 2. Remember, that's 0. Multiply both sides by 2. Divide by the acceleration in the y. Take the square root of that. That'll give me the time. So visualize that happening. Multiply both sides by 2, so the half goes away. Divide both sides by acceleration in the y. Okay, good. And then that's t squared, so I've got to take the square root of both sides. And then this thing is gone, right, because the initial velocity is 0. Okay? So 2, negative 0.61, negative 9.8. So at this point, if you would have forgotten that it's negative 0.61, the displacement in the y, you would probably realize it because you've got negative 9.8 for the acceleration in the y. So if you accidentally did 0.61 instead of negative 0.61, at this point you might realize it, I think, right? Because you'd have a negative sign under the radical. Okay, so without putting the numbers in, that's how you do this. And you can see it comes out in seconds. That meter and that meter cancels. The second squared bounces up to the top. So the answer turns out to be in seconds. And then to get the displacement in the x direction, this is the x velocity times the time. And now the x velocity, that's the 8.5 given in the problem. So you know the x velocity, you know the time, you could figure out the x displacement. It turns out it's less impressive than you would think. I think I could actually do that. Probably not, but you get a smaller number than you would think. Okay? Any questions on this one? So let's look at 3.32 from the homework. And then also a few other ones. Okay. Nope. Okay, that's what I wanted to do. Okay. A rifle is aimed horizontally at a target 48 meters away. You might have different numbers. The bullet hits the target 2 centimeters below the aim point. Okay. What was the bullet's time of flight? So how long until it hit the target? And then what was the speed that it left the barrel with? Okay, so we'll definitely need a picture for this one. So again, you might have different numbers.
Can you switch this to-
Yep. Okay, excellent. So this distance is 48 meters away. So if the bullet went straight across, it would land here, but it actually went down a small distance. And I'm just, it's not the scale. This is 48 meters, this is only 2 centimeters, right? So the displacement in the y direction, 0.02 meters. Is there anything wrong with my 0.02 meters? Should be negative, yes, because it's traveling downward. This is negative. Okay? So let's just read it again, make sure we're not forgetting anything. What was the bullet's time of flight? And that's part A. Part B is what speed did it leave? Really, that's the x velocity, because they're saying it's fired horizontally. Okay? Now, it doesn't look like we have a lot of information, right? We only know the x displacement and the y displacement. But we actually know more than we think we know. The acceleration in the y, negative 9.8, we know that. And we also know the initial velocity in the y direction was 0. Right? So you know both of those pieces of information. Because it's fired horizontally, you know the initial velocity in the y is 0. We're assuming no air resistance, so the acceleration in the y, negative 9.8. So really you have a couple additional pieces of information. When you do problems, you scan through for numbers, right? Initially, like you're reading a problem, all the numbers, especially in math or physics, jump out at you, but these two pieces you bring to the problem yourself. So this would be the same problem, finding the time, if you just thought, if you drop something, it travels 2 centimeters this way, how long does that take? So you drop something, it travels 2 centimeters, how long does that take? It's the same problem, because we can separate the y direction part of it from the x direction part of it. Okay? So remember, you have all those kinematics equations to work with. Over here on the right-hand side, we don't know the speed in the y direction, so the first one's not really going to work for us. The second one might work for us, though, because we know the y displacement, we know the initial velocity of the y is 0, so you can use the second one here to figure out how long it takes to fall 2 centimeters in the y direction. Okay, so just to save a little bit of time, that's how you would do it. Use this one. Okay, so I'll put dot, dot, dot. That means you do those steps, figure out the amount of time. Okay? So how are we going to get this part B, the x velocity? That's a hint. That's an actual, what's the line called between the numerator and denominator? I don't even know. Is there a name for that? I'll have to look it up. I don't know. So that's a hint. It's this formula, right, in the x direction. This is all you have for the x direction. Delta x divided by t. So, as I was saying earlier, sometimes you have to use y direction information to solve x direction problems. And that's what we've done here. We use the y direction to figure out the time. Once you get the time, you know the displacement in the x direction, that's 48 meters, you could figure out the velocity. Okay, so use this for part B then. It's kind of like the dog jumping problem in reverse in a way. The dog jumping problem, they gave you the x velocity, you had to figure out delta x. Here you know delta x. The first part was really the same, and then you can figure out the x velocity. So if you're playing darts, you can never aim right at the bullseye horizontally. So if there's the bullseye, if you throw it right at the bullseye, you're always going to miss it, right? Because it immediately starts descending. So your brain eventually corrects for that, and when you're playing darts, you have to give it some loft and have it come back down, right? If you shot it directly at it, you would never hit it. Okay? Very good. All right, any questions on that one? All right. Let's see what else we have here. So this one is another one here. Let's take a look at, write down what we know. A mountain lion can make a, oh, sorry. Thanks, Rick. Okay. So a mountain lion can make a leap of 10 meters long, reaching a maximum height of 3 meters. And we want to know what is the speed. So I'm just going to draw this one out and then leave most of this one to you, but we'll draw it out. So a leap of 10 meters long and a maximum height of 3 meters. What is the speed when it leaves the ground? And then at what angle does it leave the ground? Okay. Okay, so it's kind of like this picture. So this is the overall speed. This is the maximum height. They tell us it's 3 meters. And then they tell us this distance here is 10 meters. So what is the speed when it leaves the ground? So what is the overall velocity? And then also what is this angle? Okay. So let me just give you some hints on this one without completely solving it. One hint to use is this. At the highest point, the y velocity is 0. So for this problem, you'll probably have to look at the x direction, look at the y direction. You might have to mix a few things together. And then also don't forget the range equation. Sine of 2 theta divided by 9.8. And the range is this 10 meters in this problem. See, the problem right now is, if you try to solve this problem, you do know the range and you know 9.8. You don't know the overall velocity and you don't know what theta is. So you have one equation with two unknowns. Right? You can't independently solve it right now. You don't know theta, you don't know the initial velocity, the overall velocity. What you can do, though, if you ever run into this situation, is get another equation with the same unknowns, and then you could take one equation and plug it back into the other equation. So this is just from the x direction, this equation. So take a look at the y direction and try to think about it in terms of the same unknowns. So in the y direction, you know the displacement in the y, 3 meters to get to the highest point. You know the final velocity in the y at the highest point is 0. And then you know the initial velocity in the y is the overall velocity times the sine of theta. Okay, I don't want to say too much, but think about this equation, the y information. One equation and two unknowns, you're going to have to try to eliminate one of those unknowns by using the y direction stuff. I wonder if I should say one more thing. And hint. Okay, hint. This might be a good place to start.